need to connect to multiple MCP servers, remote APIs, local scripts, or both from a single client. You'll see how to configure a unified, FastMCP client that handles different transports, authentication, and environments all in one place. The pattern uses a simple dictionary to define servers, so you can switch between HTTP endpoints, local scripts, or even debug environments without rewriting connection logic. Config equals MCP servers, server name, hash remote HTTP SSE server, transport, HTTP hash or SSE, URL, https://API example.com/MCP, headers, authorization, bearer token, auth hash or bearer token string, local server, hash local stdio server, transport, stdio, command, Python, args/server py, verbose, env, debug, true, CWD, path to server. This configuration demonstrates the declarative transport abstraction pattern, where connection details and server behaviors are defined through structured configuration rather than hard-coded implementation. The pattern centralizes transport-specific parameters, HTTP headers, authentication, process execution, in a standardized format, enabling runtime flexibility without modifying application logic. What makes this distinctive is the complete separation between what servers you connect to and how those connections are established. The pattern works by treating transport mechanisms as interchangeable plugins, with the configuration acting as a contract between your application and available transports. Each server definition becomes a self-contained profile that specifies transport type, credentials, and execution context, while the client framework handles protocol negotiation and connection lifecycle. This design enables dynamic multi-server routing, where tool calls and resource requests are automatically prefixed with server identifiers, creating a unified interface across heterogeneous backends. This approach solves the problem of environment-specific coupling in distributed systems. Instead of maintaining separate code paths for local testing, cloud APIs, and process-based servers, you define the environment in configuration and keep your application logic transport agnostic. It's particularly valuable for testing, swap real servers with in-memory instances, multi-service architectures, compose tools from different servers, and deployment flexibility, change targets without code changes. The trade-off is initial configuration complexity, but the payoff comes in reduced maintenance as your system scales across environments. Let's break it down line by line. Config equals. This initializes the configuration dictionary, the single source of truth for all MCP server connections. Centralizing server configurations here prevents hard-coded values across the codebase and enables environment-specific overrides. MCP servers defines the MCP server's configuration dictionary, mapping server names to their connection parameters. This centralizes server configurations for different environments, enabling runtime selection between remote HTTP servers and local stdio processes. The pattern supports both production and development workflows in a single config structure. Server name. This defines a named server configuration entry. The key, server name, acts as an identifier for this specific MCP server configuration, allowing you to reference it elsewhere in the system. This follows the standard dictionary pattern for named configurations, enabling multiple server setups in a single config file. Hash remote HTTP SSE server. Transport, HTTP hash or SSE. This defines the communication protocol for the remote server. The HTTP transport uses standard HTTP requests, while SSE enables server-sent events for real-time streaming updates. This pattern lets you switch between polling and push-based communication without changing client code.
URL: https://API example com/MCP.
This specifies the HTTP SSE server endpoint. The URL defines where the MCP client will send requests and receive real-time updates, establishing the connection point for all remote operations.
Headers, authorization, bearer token.
This defines HTTP request headers, specifically adding an authorization header with a bearer token. Required for authenticated API endpoints, it ensures the server validates the client's identity before processing requests.
Auth, OAuth hash or bearer token string.
This specifies the authentication method for the remote server connection. Using OAuth delegates to the OAuth2 flow, while a direct bearer token string provides immediate authorization. The config supports both dynamic token exchange and static token injection. This closing brace terminates the local server configuration block, completing its definition in the MCP servers dictionary. It maintains proper JSON structure, ensuring the configuration remains valid and parsable. Without it, the dictionary would be malformed, causing runtime errors during server initialization.
Local server.
This defines a local server configuration entry, contrasting with the remote HTTP SSE server. Local servers execute as subprocesses, enabling development and testing without external dependencies. The pattern mirrors production server structure, but runs commands directly on the host machine.
Hash local stdio server. Transport, stdio.
Specifies stdio transport for local process communication. This enables direct interprocess communication via stdin/stdout, eliminating network overhead for local development and testing. The pattern is common for CLI tools and local debugging scenarios.
Command, Python.
Specifies the executable command for the local stdio server. This is the entry point that launches your server process, with subsequent args passed to it.
args/server pi, verbose.
This specifies command line arguments for the local stdio server process. The array /server pi defines the entry script, while verbose enables detailed logging, critical for debugging server-side issues during development. This pattern mirrors how you'd invoke the server directly in a terminal.
Env, debug, true.
This defines environment variables for the local server process. The debug equals true setting enables verbose logging, critical for diagnosing issues during local development. This mirrors production's environment variable pattern, but scoped to this subprocess.
CWD, path to server.
Sets the working directory for the local stdio server process. This ensures all relative paths in the server's code resolve correctly from the specified directory, preventing file-not-found errors when the server tries to access local resources. Critical for servers that need to load files or reference paths relative to their installation location. This closing brace terminates the local server configuration block, completing its definition within the MCP server's dictionary. It maintains proper JSON structure while separating this server's stdio-based configuration from other server definitions. This closing brace terminates the local server configuration block, completing the definition of its transport, command, and environment settings. It maintains proper JSON structure while separating this server configuration from other entries in the MCP server's dictionary. The pattern ensures each server configuration remains isolated and independently modifiable. This closing brace terminates the nested server configuration dictionary, completing the definition of all MCP server configurations in the config object. It maintains proper JSON structure while allowing additional top-level configuration keys to follow if needed. Transport configuration patterns. The MCP configuration format bridges local subprocess execution and remote HTTP SSE communication through a unified schema, where transport type determines whether your server runs as an isolated process or a network endpoint. Environment variables passed via env only exist in the server's isolated context, never inheriting from your shell or leaking back to the client. This dual-mode design lets you swap between local development and cloud deployment without changing your client code.
The configuration that names the transport becomes nameless to the protocol.